Hello everyone, in this video we're going to cover the pore pressure and geomechanics module. So let's get started. So to get to the geomechanics and pore pressure module, come here to your module selection menu and choose geomechanics and pore pressure. So within this module there are several different tools that we're going to be looking at. So first of all we're going to be looking at the brittleness. We're also going to be looking at the reservoir pressure as well as the potential continuity. So with respect to what we want to analyze on, once again, we need to decide, what we want to look at with respect to reservoir, and we're going to set this at net reservoir. And this is what is coloring up here in our reservoir plot. And really the goal of this plot is just to help the petrophysicist or geoscientist get a better understanding of what we may be able to access with the wellbore. So in terms of brittleness method, we have the Simpleton, Jarvie-Dahl, and Wang-Gale models. Depending on how you've done your analysis, you may need to choose whether or not you want this to be done based off the results from the inversion or the Roma-Yuma method. By default, we use the inversion, and by default, we use the Simpleton method, which is from Danomics. You will also need to, and once you've set that up, that will calculate your brittleness curve and help you understand where you may have potential frac barriers in your reservoir. So for example, let's switch to the Wang-Gale method. And when we do this, what we can see is that we come up with a lot of frac barriers because the Wang-Gale method considers calcite to be a non-brittle material. Same applies to Jarvie-Dahl. So that's why the Simpleton method, which is really only interested in understanding the clay volume and the kerogen volumes, works better in this system. Now you can come in here and you can set your brittleness cutoff factor, and we're going to say at brittleness, we're going to say less than, let's say, 0.4, which would actually eliminate a lot of the frac barrier here, or we could set that at a higher value, so like let's say a 0.75, and that would tell us that we have a lot of frac barriers. So we're just going to go back to our default of 0.5 here. And now we can see that we do have some frac barriers in our interval, but not many. And then it asks us what's the minimum thickness of reservoir, and how much of a discontinuity can we have between reservoir intervals, and what thickness we need to have to be a real frac barrier. So let's say that we need 15 feet to be a real frac barrier. And in doing so, we'll see that we're going to have some changes here in what's defined as a frac barrier. Let's say we can frac through 50 feet of just non-frac barrier, non-reservoir interval. And let's say our minimum reservoir interval needs to be at least 5 foot to really get our attention here. And now what this is telling you is that, hey, you could come in here and drill a horizontal well in the Eagleford, and there's a very good chance that it will connect up into the Alston Chalk. And that if you drill a well in the lower Alston Chalk, there's nothing that's going to stop your frac from propagating into the upper portions of the Alston Chalk. So that's all we're trying to show with our brittleness and our reservoir continuity analysis. So that's one half of the module. And what goes along with that is if you had a shear sonic log, you would get calculations for the Young modulus, bulk modulus, shear modulus, and the Poisson's ratio. But this well does not have a shear modulus, so that's why we're not seeing those curves. So we're going to zoom out a little bit, and now we're going to focus on setting our pressure. For our pressure methods, we have the Eaton sonic and resistivity methods, both in the modified and unmodified formats. And so we need to enter some parameters in here. So for example, what's our hydrostatic pressure gradient, our lithostatic pressure gradient. And when we're analyzing these methods, we typically only want to calibrate ourselves in the shell intervals, and so we can define where our V clay cutoff is, and that's what helps us guide what we need to look at with respect to this analysis. So with the Eaton sonic method, we have a couple of parameters here to set, the Eaton exponent and the normal compaction trend. And so what you're really trying to do is you just want to fit this normal compaction trend line through the Shayley intervals, and that will calculate your Eaton sonic here, which is shown in the green line. And we can see that we already have a pretty good match through a lot of this interval. There may be some interval down here that we could try to match as well. So we could, we could try modifying that trend line a little bit and see how that changes our analysis. And it's really one of those things where there's just a little bit of trial and error to try and get it to fit through there and to understand how you're changing some of these parameters. And so you can also try the modified Eaton method. Here we have slightly different parameters, but the idea is the same, is that we want to come through this compaction trend line. So we can change our B exponent, and that moves this curve left or right. We can also set this DTO, which is originally kind of a mudline sonic value, as well as modifying our Eaton exponent here. Oops, sorry, I clicked off on a different project by accident there. So we can change these values to change the slope of this line and try to see try to see how we're affecting our analysis here. Yeah, and so actually we just moved that the wrong way. So this is the general process that one uses for this, and we can start to see that we're getting a we're starting to get a fit. We can start to see this compaction trend line moving around here. There's it is quite sensitive to the values you put in here, so it's going to take a little bit of trial and error to really get this nailed down. But then what you'll see is that we are essentially on a normal trend line here, normal pressure trend line, based on our results here, with maybe the slightest amount of overpressure showing up in our Eagleford. So once we're happy with that, we then want to go through and calibrate our resistivity. Really the same thing here. We want to set our normal resistivity value. So trying to match that here in the shells. And we see we get a pretty good fit here, and we're getting normal resistivity values. However, we see down here in the Eagleford, it's calculating abnormally low resistivity, and this is very common in organic shells. And this is because organic shells have excess resistivity associated with them, so we often get quite a poor solution there. And then which one do we want to use for our final pore pressure solution? Well, you can come here and use this selection menu to select either the sonic or the resistivity methods. And when you do that, we will calculate an overpressure curve for you. And in this case, it looks like the sonic is giving us a much more believable solution. Okay, so that was a quick overview of the Geomechanics and Pore Pressure module. I hope you enjoyed this video, and as always, remember to save your work.